All right, you guys, today we're looking at how to prove triangles are congruent with certain information. And we're starting with SSS and SAS. So first, I'm just giving you this little note at the top. A triangle is unique if only one triangle can be drawn from the given information. So any triangle that has that same information would match the first one perfectly. They would be congruent triangles. So the first combination that we see show up that works is side, side, side. So SSS for side, side, side. So if three sides of one triangle are congruent to three sides of another triangle, then the triangles are congruent. So the way that I've drawn these figures is trying to show them kind of rotating around this fixed point here, where this segment would rotate into this position here. I'm going to give it a single tick mark. This segment would rotate into this position here. I'm going to give double tick mark. And then this last segment would rotate into this position right here. So I'm giving that a triple tick mark. So if I can identify that I have three pairs of corresponding sides that are congruent, then my triangles, they have to be congruent as well. And when I write a congruent statement, order matters. So let's say that I name that first triangle, triangle BOX. So I'm starting at B. I'm going to put a little dot here at B. So B is right in between what I have as my double and single tick mark sides. So that means over here, I'm starting at that same location, single double, right here, C. So I start with C. And then if I'm going B to O, I'm going C to A and then R. So here, as you can see, I made a little word, box and car. So box is congruent to car. So why that's so important, why keeping the order matters, is because I can also read this statement back and see how my sides link up, how my angles would link up too. Okay, the second one that we're presented to right here is side, angle, side. And there's a reason the A is right in between. So if two sides and the included angle of a triangle are congruent to two sides and the included angle of another triangle, then two triangles are congruent. So that included part means it has to be between the two known sides. All right, so my picture here, I've kind of drawn it as a reflection, where this would be my mirror line. So let's say that I tell you that these segments are congruent, and then so are these. So here's my two pairs of corresponding sides that are congruent. So if I need the included angles to be congruent too, that means it has to be P and S just like that. So now I can write a congruent statement. I can say that triangle PIE would be congruent to triangle. Well, if I name it from P to I, that means S to K, and then finishing with the Y. So I'm linking it up in the same order. Right? So when I read it back, I can see which corresponding angles would be congruent, which corresponding sides would be congruent as well. Okay, before I go any further, I just want to show you how each of those combinations is unique. Let me pull this aside. So say I know three sides of a triangle. So here are my three sides. I have a side that's 8, a side that's 7, and a side that's 6. So let's say that I put my big side up top right here. Here's my 8. Let me zoom out just a little bit so you can see those edges. Okay, so here's my side that's 8, my biggest side. So my other two sides, they're going to have to fit just like so to make a triangle. So just like that, there's my triangle. I could rotate it, I could reflect it, I can move it around, but ultimately it has to look like this. So this is a unique triangle because I have 3 measures. It locks it into a rigid position. Any other triangle with that same information would have to be congruent to this one right here. Let's say I do the same with side, angle, side. So let's say that I know that there's an angle of 45 degrees. And I have the 2 sides that sandwich that angle, like this. Let me slide that up so you can see it. So if I have this much information right now, I have 2 sides and I have the included angle. Well, that 3rd side, it's going to have to fall in right here. I have no other place for it to go, right? It has to be right there, from there to there. There's no other place that it can be. So that tells me that knowing my 2 sides and the included angle locks my triangle into a rigid, unique position. Any other triangle with this information would match this one perfectly. Even if I reflect it, rotate it, translate it, move it all around, it's still going to be identical to this triangle right here. All right, so now let me go back to our outline and show you that we have 2 cases that do not work. Let me zoom back in tighter. So these are 2 combinations that do not work. So one is 3 angles. So if I know that I have 3 angles of one triangle congruent to 3 angles of another triangle, then the triangles are not necessarily congruent. And I'm illustrating that right here. They can be dramatically different sizes. So if I only know the angles, I can scale my triangle up or down, right? They would be similar, but they are not going to be congruent, not necessarily, right? There are many triangles that we could create with the same information. So I'm going to go like this, do a little cross off of AAA, right? Angle, angle, angle. It does not work. We know that there are many different triangles with the same information. Okay, and then the second combination that does not work is side-side angle. So side-side angle, what's important here is where the A is. It's the not included or non-included angle. And regardless, it's not going to work. We'll cross off there. So if 2 sides and the non-included angle of a triangle are congruent to 2 sides and the non-included angle of another triangle, then the triangles are not necessarily congruent. So what's happening, so look at this big triangle right here. We know 2 sides and the non-included angle. So what ends up happening is that the angle right here where B is, so I'm going to put a little dot at the vertex of that angle. So what happens here, since I don't know that angle measure, I get a hinge right here where B is. And this measure here, this side, this measure is set in stone. Okay? And it can swing into a second position right here while it keeps the same measure here, the same angle here. But since I don't have the angle here in between my 2 sides, it does not lock into a rigid position. So this side swings into an alternate position right here, making a very different looking triangle. So the hinge would be right here for this second triangle as well. So what we say with side-side angle is that it suffers from this swinging door effect because we have 2 very different triangles that could be drawn with the same information. So I'm going to write that out as swinging door effect. Right, where we have 2 very different looking triangles with the same information. Okay, so those are the two combinations that do not work. Angle, angle, angle. We have many, there's an infinite number of triangles we could create with just the information about the angles. And if we have side, side, angle, there's two very different looking triangles. We see that this side right here, right, it could swing into a second position, making it look like this instead. So that's what's happening when it's not the included angle. It has to be the included angle to lock it into a rigid position. All right, example 1. So here we're going to go through and we're going to look for, do we have enough information to determine whether the triangles are congruent? All we know right now are side, 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 and side, angle, side. We will have 3 more combinations that work coming at us next lecture. So if we can say yes, we're going to complete the congruent statement, state which reason, is it side, 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 or side, angle, side. If the angles are not congruent, we're going to write not congruent. Okay, so some of these we have to connect a dot. So we have to make a connection as we work through. So here in this first one, I can see that, oh, I have this common side right here. I can give that a triple tick mark. It's the same side for both triangles. My reason would just be the reflexive property of congruence. I'm going to write that down just so we can start to see how we're making these connections, because we're going to have to prove them really soon. So this would be reflexive property of congruence. And now looking at my picture, I have 3 sides marked for both triangles. So my triangles are congruent by side, side, side. Now how do I finish my statement? So if I start with P, P-O-S, P-O-S. So over here, it's got to be with T, T-O-S, right? I'm trying to make sure I line them up and I state them in the appropriate order. Okay, next one. Here, I'm only given 1 pair of sides that are both parallel and congruent. So if I build off of those parallels, you guys have seen me do this before. Let's build off these parallels here and here. And if I view this as my transversal, I can see a pair of alternate interior angles. So here and here. So I can link up those alternate interior angles because of the alternate interior angles theorem. I also see a common side right here, so I can give a double tick mark right there. That is the same side for both triangles. So that's the reflexive property again. All right, now I want to go back and clarify one extra thing. If I was to write how this side would relate to itself, so for this triangle, the one on the left, if I'm reading it S to O, how would I read it for the triangle on the right? It would also be S to O. Now over here, it's different. Over here, SO was a line of symmetry. I can see how this triangle reflects onto itself on this side. Over here, it is not, right? It's a rotation instead. This triangle can rotate into this position 180 right over here. So if, for this triangle on the left, if I name it SW, I'm naming it from the angle that has 1 tick mark to the one that's not marked. So over here, that would be W to S. The order flip-flops, and the order is important. So it would be SW to WS. All right, so now do we have enough information? We should. We have side, angle, side, right? Side, angle, side, SAS. And if I call the first one SWO, the second one would be WSH. Order matters. All right, next one, looking at C. So here, the only thing that I can build off of are the vertical angles. So I can give little marks here. Vertical angles theorem. Okay, But do I have one of those combinations? Do I have side, side, side? Do I have side, angle, side? And I don't. What I have is SSA, right? I don't have the included angle. So the reason that that does not preserve congruence, that does not establish that one triangle is unique, is right here. So look at where S is, right? That's our hinge. And this side right here could swing into an alternate position about right here and make a very different looking triangle. I usually show this with a construction. I might make another video just to illustrate that swinging door. So we know that SSA does not establish congruence. So I really cannot say that my triangles are congruent. They are not congruent, not necessarily congruent. I'm just going to cross off those two spots. I cannot finish up. Side-side angle does not establish congruent triangles. Okay, next over in D, well, I got a lot of triangles here, so I got to look at what is it I'm asked to link up. So I'm asked to link up REC. So here's REC, so I must try to sync it up with this triangle over here. So what can I connect? I can connect the vertical angles again. So here. So my reason would be the vertical angles theorem. And then what do I have? I see that I have side, angle, side. So if I call the first one here REC, then over here that has to be HEO. Okay, and I'm just showing you also that this is a parallelogram. In a parallelogram, the diagonals bisect each other. So I'm just showing you that we have these triangles embedded inside that end up being congruent. Okay, next up, here in this figure, I can also connect my vertical angles. So again, I'm just keeping an eye on what am I trying to sync up, DCO. So this triangle would have to sync up with this one right here. So I can again link up the vertical angles. It's a common reason that we see. So vertical angles theorem would be the reason. And if I call the first triangle here DCO, I see I have side, angle, side, right? So DCO would sync up with DSE. So I have side, angle, side. And to finish this statement would be DSE. This is meant to be an isosceles trapezoid. And what I'm showing you here is that my diagonals, when they cut through each other, they're still congruent here, here, and here, here. So I can see that I have an isosceles triangle that's formed here, here as well. These two triangles end up being congruent. Okay, next I'm saying that spider, so spider is a regular hexagon. So that means that all sides are congruent and all angles are congruent as well. So if I'm trying to link up these two triangles, I can give tick marks to all of my sides. I'm just going to mark the ones I need, and my angles as well. So right here, angle P would have to be the same as angle D. So I have two triangles that are congruent. They're both isosceles. So I could use side, angle, side. But when I name this first one SPI, I can name the second one EDI or IDE. I have a little bit more flexibility because it's isosceles. I'll go with the first one that I said. And here could be IDE also, because it's isosceles. All right, I'm going to mark my little arrow right there. Okay, so now we're going to do some formal proofs. So on this side, I kind of did a little mini proof with you as we were going through, just trying to show you the reasons for how I'm able to connect other angles, other pairs of sides. And now we're going to formalize it on the back. So I picked 4 proofs in class. I might not go through all of them, but we'll see what we just have time for. I'm going to prove them all for you here just so you can see them, and I'm going to zoom in really tight. All right, so we're going to prove the triangles are congruent using side, 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 or side, angle, side. Those are our only options right now. So here for the first one, I'm given 2 sets of corresponding sides are congruent, and as I write it, I'm going to mark up my diagram as well. So I have 2 givens. Neither of them is going to lead me anywhere else, so I would probably lump them together. This is the area where I do start to split apart the givens, really only when I can see that there's a reason where it's going to connect me to something else. All right, so here my reason is just given. It is given to me. So here, here, and here, here. So really what we're trying to prove is that a parallelogram gets split into 2 congruent triangles. So right now I have 2 pairs of corresponding sides that are congruent, and I need to link up the 3rd pair or the included angle if I can come up with a reason. Now I can see that it's a common side right here, so that's the reflexive property. So let's say that I name it for the triangle on the left as PR. How do I name it for the triangle on the right? So if I'm reading it for this one, and I'm reading it from P to R, notice how here I'm in between the 2 and 3 tick mark sides. Over here, I need to start in between the 2 and 3 tick mark sides. So I start with R, and I go to P. So PR is to RP. Reflexive property of congruence. Right, we're just saying it's the same thing as itself. Reflexive property of congruence. And now I've linked up all 3 pairs of corresponding sides. I've shown that they are congruent. I can reach my conclusion. This is pretty short and sweet. So I can say that triangle PKR is congruent to triangle RAP. Side, side, side. All right, one other thing that I can do to show you why that flip-flops, if I go back to how these triangles are congruent, right, remember how this one rotates 180 into this position right here. So if I look at my statement, it always shows me how my parts link up. So if I read it in order, P to R, just like that. So PR. It's going to show up in that same order over here, R to P. So you can see how it flip-flops, right? PR, here's RP, just like I have it here. All right, next one up. So here I have 2 givens. Here I will split them up because I like to see how my information builds. So I'm going to start off with that first statement. Point N is the midpoint of BR. Given. Okay, if I'm told that something is a midpoint, what does that mean? Well, if something is a midpoint, it bisects a larger segment. So it splits this segment here into 2 congruent parts. So that leads me to BN is congruent to RN. My reason, it's simply what it means to be a midpoint. So definition of midpoint. All right, next up, I'm kind of at a dead end. So I look at my other given. What does it say? All right, well, it tells me that BNA is a right angle, and so is RNA. So I'm just marking it with that box notation, and I'm just going to write that right here. So angle BNA and RNA are right angles. Given. All right, this next step might seem silly, but even though I've stated that they're right angles, I still have to show that they are congruent. And I know that all right angles are congruent, so I'm just tying up that loose end by stating that angle BNA is congruent to RNA. Right? Right angles are congruent. I could also just say definition of right angles. Okay, if you like just writing a sentence, I'm okay with that. I will take it also. Okay, I'm looking for another connection. Right now I have one pair of corresponding sides, one pair of corresponding angles, and I see, oh, reflexive property again, right? I can link that right back to itself. So if I name it as AN for this triangle on the left, it is the same order as the one on the right. So A to N is the same here, A to N. And my reason would still be the reflexive property of congruence because I'm linking something back to itself. And now I have two pairs of corresponding sides, one pair of corresponding included angles, so I can reach my conclusion here in step 6. I can say that triangle BAN is congruent to triangle RAN. Side, angle, side. We end up seeing a lot of side, angle, side in these proofs. All right, let's look at C. All right, so in C, again, we have two givens. So I'm going to start with the first one and see where it leads me. So I'm told that PN bisects AK at point R. Given. All right, so if PN, if this segment bisects this segment at point R, that means that AK is being split into two congruent parts right there. So now in step 2, I can say that AR is congruent to KR. So AR to KR. Right? That's what it means to bisect something. It creates the two congruent parts. So definition of bisect. Okay, so now I'm stuck, right? So I'm going to go look and see if I have another given that can help me. And I do. So it's telling me that PR is congruent to NR. Given. So double tick mark, double tick mark. Okay, so I have two pairs of corresponding sides that are congruent. I still need either the third pair of sides or included angles. And that is pretty easy for me to see that, oh yes, I have these vertical angles right here. So here I can say that angle PRK, so PRK will link up with NRA. Right? We know that's the vertical angles theorem. Okay, so now I have side, angle, side. I can reach my conclusion and say that triangle PRK is congruent to NRA. Side, angle, side. Like I said, we see a lot of side, angle, side. All right, last one, D. So D, we're told that REA, this triangle here, is isosceles with base RA. There are two things that we take from isosceles triangles. We know that that leads us to two congruent sides or two congruent angles. It really depends on what we're going after. So first thing I need to do is really look at which triangles am I trying to link up. So RAG, so that's this big one here. And then ARP, that's this big one right here. So whenever I'm looking at something where there's overlapping parts, sometimes it helps to just pull them apart and view them as two separate triangles. So I'm just going to draw them as two separate triangles off to the side. So here is G, R, A, and here is P, R, A. Okay, so I'm focusing on what my end game is, and I have to figure out how to use the isosceles information. So linking up these two sides really is not helpful for these triangles, right? It doesn't lead me anywhere for these two triangles. So it must be these congruent angles that's going to be helpful. So first, let me just write that first given. Triangle REA is isosceles with base RA, given. Now again, remember I'm building off of the sides or the angles, and it's the angles that are going to help me here, here, and here. So where are those two angles in my big diagram? Here and here. Well, this angle right here is this angle right here. And this angle right here is this angle right here. So I can make a connection between angles. I can say the angle, let's see, angle GAR is congruent to PRA. So here I can say, well, because my triangle is isosceles, I have two base angles that are congruent, or two angles congruent. Okay, now I'm kind of stuck. I can't use anything else for my isosceles. Knowing the sides doesn't help me here. It would help me if I was proving these two triangles congruent here and here. All right, so I'm looking for something else, and I have another given, so might as well throw that in and then stare at my picture another time. So here we're told that GA here is congruent to PR here, right? That was given to me. So right now I have two pairs of corresponding sides that are congruent, one pair of corresponding angles that are congruent. So I need to look for my other pair of sides. And what I should recognize is right down here, this side right here, RA, is the same side for both triangles. So I'm going to give it a little tick mark here, double tick mark, and then add that to my picture over here. Right? This is the same side for both of those triangles. So again, reflexive property, I just have to figure out what's my order. So if I call it RA for the triangle on the left, R to A, so unmarked angle to the single marked angle, here I have to name it A to R. So again, reflexive property of congruence. And now I've done my job. I've linked up side, angle, side. So I can reach my conclusion here in step 5, that triangle RAG is congruent to triangle ARP. Side, angle, side. So in all of these, I'm starting off with my given. I usually take one of them. I see if it leads me anywhere else. When I get stuck, I pick up the other given, see where it leads me to, and then I look for certain things in my picture. Do I see a common side? That would be reflexive property of congruence. Do I see vertical angles? Right, that would tell me vertical angle theorem. Do I see alternate interior angles? That would be the alternate interior angles theorem. So lots of things to work for, but we usually give you enough in the given to certainly get you started. All right, have a good rest of your day.